I'll introduce our next speakers. This talk, we've got two. They're going to tag team this presentation on some new work, new exciting work that's been done the south end of the Salt Lake Valley. First up is going to be John McLennan. So he's been a faculty member in the Department of Chemical Engineering at the University of Utah since 2009. He has a PhD in civil engineering from the University of Toronto, which he was awarded in 1980, which is before I would have taken any schooling coursework. It's before I was born.
Don't rub it.
You're next. No, he's next. Before joining the university, he had nearly 30 years of experience with petroleum service and technology companies, including Dow, Schlumberger, Cheritech, Advantech International, and ASRC Energy Services. He has worked on subsurface energy recovery in a variety of reservoir environments throughout the world, particularly geothermal energy for the last decade. He is a co-principal investigator for the Utah Forge project. He is an American Rock Mechanics Association fellow and has served as ARMA president. He is also a member of the Utah Academy of Engineering and Science. It's our first.
And you want to introduce Cary Smith now, or do you want to wait?
You want me to? Or I can wait.
Okay, maybe we'll wait.
Okay.
I'm under strict instructions. I've got 12 minutes. And so don't worry, this is not going to be a metaphysical discussion. Okay, what we're going to talk about is the point that we know, the point of the mountain. And we're going to talk about recent work that we did in response to a state of Utah award to do a feasibility study for various water and heat uses at the point. And as most of you are familiar, certainly, we're talking about down here where we can see the Traverse Mountains and the Wasatch Range here. So right in here, and you can see a concealed fault that's being inferred at this point here. So a relatively complex location, which has had geothermal production from down in here for quite a number of years. And this is what it sort of looks now. To put it into perspective, this is Bangor Highway, and this is I-15 right here. And so that's the location of this. And this was the location of the former state prison, as you can see in this picture. And the goal of the state, as they're going from a pseudo greenfield operation, is to evaluate effective energy usage, taking advantage of natural resources that are there. And so there was a feasibility study where a well was tested to see what sort of productivity there would be. We quantified the geothermal resource, and frankly, this was based on summarizing a lot of work that had been done by the UGS, or the UGS's predecessor, in 1979. Great paper by Murphy and Gwynn summarizing this, and that's what a lot of this is based on. There was supplementary work in 1980 in the DOE contract at Cheritech, and then Morrison Knudsen did a study around about 1980 as well. And so pretty much what I'm going to talk about is just a synopsis of work that's been done previously and a little bit of what well testing we did. So looking at the resource, trying to look at what happens when you imagine a new infrastructure put in here, as is envisioned by the point of the mountain development, and mapping this out on a district scale and looking at feasibility and preliminary evaluation of some of the issues that are associated with it. And so we go from this, and as you saw now, there's not much left of the original infrastructure, and you're envisioning going to something like this. And there is a plan forward for going through with this. And one of the components is to just assess the feasibility of using ambient thermal loops or similar technology for heating and cooling this operation. And so for quite a number of years, we've known that there are springs here. As a matter of fact, the prison was heated for a number of years with hot water. There were tropical fish grown by the inmates at the prison and sold. So if you bought a little fish back then, it might have been an ex-con. But anyways, Crystal Hot Springs has been known for a long time. And as I said, Murphy and Gwynn, that's the sort of standard study that you look at. And it's inferred to be a deep convective system. And it's squished between a couple of rangefront faults, and it occurs beneath tertiary and quaternary valley fill sediments. There's meteoric water is inferred to have gone to depths of 2 to 3 kilometers. And in the process of moving in there, it's heated up and it's recovered through a fault system to the surface. And in discussing this with Christian, he's put forward a hypothesis that the meteoric water is not necessarily going down the Wasatch Front immediately adjacent to this, that it may be coming in from farther south. And if there are questions on that, I'll let him defend his hypothesis on his own. But nevertheless, you know, the geothermometry suggests those sort of depths, and it's coming to the surface. And so it moves upwards, probably along fault boundaries, and it comes to the surface and it reaches a fractured quartzite, the ochre quartzite. I think it's Pennsylvanian, maybe Permian. I'm not 100% sure, but it's fractured and it spreads out through that, and then it probably disseminates upwards through the alluvium, and it's expressed in the springs. And so this is the vision that was put forward, you know, 40 odd years ago, that here is the original state prison, and just based on a network of monitoring wells and some deeper wells that existed, various blocks were drawn. So block A, block B, this is sort of the heart of the whole system. And it's often inferred that, you know, this is where much of the activity is going on, with possibly some possibilities for accessing the resource in this block A. Limited opportunities here and limited opportunities to the north because of some of the fault boundaries that are inferred to exist. But what has also been seen is that in the alluvium, if you go down to about 200 feet, and that's still well within the alluvium, the quartzite is maybe somewhere between 300 and 500 feet before you reach it. In the alluvium, I think we're having an earthquake. In the alluvium, you can notice these contours of temperature. So this much here, that's 1,000 feet. And so you can see that contours of 30 degrees C are, you know, 1,500 feet from this sort of the heart of the geothermal operations. And so there's possibilities for a couple of things here. You can extract heat from the geothermal wells in general, or there's a possibility of borehole thermal storage if you're drilling wells and acquiring, at least for heating, acquiring heat in those areas that are more than, say, maybe 40 degrees C. So these are some of the things that one takes into account. So if I superimpose this upon a plan of the future development for the point of the mountain, you can see we're sort of down on the southwestern edge of it, where that prominent geothermal zone, fault-bounded geothermal zone is, and this is probably a 40 degrees C temperature contour. So opportunities for direct heat and for borehole thermal storage in this regime. So the state of Utah recognized the opportunities here, and a lot of this may have been driven by Mr. Goddard's office. And so as I mentioned earlier, one of the first things that was done was to test the existing well. Well, I could never figure out a name for this well, so I just called it well 2126 after its well identification number, and that's sort of the way I'll refer to it. There was a previous well there that had serviced the prison. You can see USP, Utah State Prison, test hole 1. And that well, eventually, a lot of testing was done on that in the 80s, and that well eventually corroded and was abandoned. And this well, 2126, was drilled in 2010, was completed in 2011 with about, 120 feet of slotted casing at the bottom of the well. And It was pretty good. It recorded temperatures that were in the range of 175 Fahrenheit. Some other wells in the area that had been serving some local businesses, Utah Roses, got a little higher than that, but this is about the temperature we're anticipating. And it produced 350 to 500 gallons per minute. We went in August of this year and tested this well to try and understand, what the capacity of this well is for producing water for a development that was as large as this. And one of the things before we even went in is that there was anecdotal information that the production of this well had slowed down after the McLennan earthquake. We didn't really see evidence of that when we tested this well, but nevertheless, it's just something that is there. And this was still slightly artesian when we came into it. It was, about a foot above ground level. So we drilled. We didn't drill the well. We tried to pull the pump out of the well. And so the pump had been in the well since 2011. It was pretty much corroded, and the pump shaft broke, and so the pump dropped to the bottom of the well. But story of my life. About 360 feet of well was available for production, and so that was cool. And so the first thing that was run was a step drawdown test. What people do with a step drawdown test is they progressively increase the rate that they produce the well at, and they look at how much it is drawn down. So if we look at drawdown, that's the depth of the phreatic surface below the wellhead. This is going from 0 to 60 feet down. And over time, we can see that we started out at 130 gallons per minute and progressively increased the rate up to 600 gallons per minute. The allocated production, and I forget the term for this well, would be 700 gallons per minute. That's what could ultimately be taken out of this resource. And you can see that it pretty much held up. I mean, the drawdown increased down to about 50 feet of drawdown. About 50 feet of drawdown. And so this was a successful test. And it also identified that we could produce this reservoir at 600 gallons per minute, could produce the reservoir at 600 gallons per minute. So based on that 600 gallons per minute, we did a constant rate test where we produced this well at 600 gallons per minute. And you can see what happens at the top. We've got the drawdown. That's the depth below the surface that the free surface of the water was at. There's about 60 feet here. Temperature declined very slightly over 24 hours, went from 181.5 to 181. So that's cool. Strong production from the well. And so it looks like it's feasible to use this reservoir. And then that basic information is used in determining the hydraulic conductivity. I'm not a specialist in this area, but I understand that these are very promising values in terms of producibility from a reservoir such as this. So we have a well. We've tested the well for deliverability. It seems okay. We've also evaluated the temperature of the well. You can see that the temperature here, and this is 180 degrees Fahrenheit right here. It's 100 degrees at the origin. And so you can see the temperature proceeding with depth down to 300 odd feet. It's getting up to in excess of 180 degrees. This is great. This is great. We also took water samples, and we determined from geothermometry that the quartz geothermometry was right in the range that we're talking about. And so it's a promising resource from the potential of rate and temperature. The water quality that was evaluated was reasonably favorable. It was somewhat rich in chlorides, and certainly there was a fair bit of sodium, calcium, potassium, and magnesium. And so we had Stuart Simmons from EGI take a look at this, and he's suggesting that carbonate scaling is a potential, and I'll show that in the next slide. But it can be minimized by not separating the gas from the water, keeping the carbon dioxide in the water, which is sometimes counterintuitive. And so Stuart did an analysis looking at the saturation indices, And so for folks that aren't familiar with this, if the saturation index is greater than 1, that means that the fluid is supersaturated and it'll be prone to precipitate. And so you can see dolomite, calcite, and siderite all are things that are going to have to be considered in terms of this. But this is standard fare in geothermal engineering, dealing with situations like that. And it may be reduced if you have a closed loop system. So what does this look like? We played around a little bit with trying to model this, and I think that this sort of these bullets sort of describe what we think is going on. Is that there's recharge down low, whether it's from the east or the south, we'll leave that to be yet to be determined. It's probably chimney-like fluid motion up, possibly an intersection of faults, but dominantly in one particular area. It gets to this fractured quartzitic zone, and then it spreads out, and then it ultimately finds ways to express itself. And in the past, that was in the ponds that were there and things like this. So chimney-like motion, limited region, as we saw in that triangular area, and maybe a little bit off to the west of that, feeds the ochre, pardon the spelling there, ochre quartzite. And if there are future wells, and this well will need to be replaced, it'll have to be re-drilled. And they should be in that premium area right around it here. And of course, this is all speculation. So what are the ways that this asset can be used? We're suggesting that an ambient thermal loop can be used, which is a large loop that circulates medium temperature water and takes advantage of various assets, such as the geothermal well, these boreholes that are drilled. And this is what my colleague Cary Smith will be talking about. But if fluid is produced from this geothermal well, we anticipate reinjection so that it'll be non-consumptive. And we'll work with the heated area for borehole thermal energy storage, and all of this. Each one of these will be a component to a loop that will be used for heating and cooling. The only caution with all of this is that, you know, there's a water allocation of 700 gallons per minute. We ran a 24-hour production test, and it looked that things were fine. But the previous reports by Morrison and Knudsen back in 80 and 81 suggested that other wells were being depleted if you pump at 700 gallons per minute. So additional testing will have to be required and monitored in any existing offset wells, just to see whether or not this can be sustained for the 30 years of application. And so that's sort of my part. It's a fantastic resource, a lot of opportunities, and I'll turn it over to my colleague Cary Smith.
So our next presenter is Cary Smith. Cary owned and operated Applied Drilling Services, a drilling, engineering, and related fields company in the oil and gas industry from 1972 to 1997. During that time, his specialty was advanced and high-temperature drilling fluids and drilling optimization. Cary has worked in the geothermal and ground source heat pump industry since 1997 and has been involved in the design and implementation of over 50,000 tons, 175 megawatts thermal of installed capacity in North America. He is president and CEO of Sound Geothermal. Cary pioneered many hybrid and district energy systems. His projects range from HUD housing to industrial facilities and university campuses to NASCAR facilities. Cary is a founding member of the Gray Edge Group and specializes in ground source heat pump ambient temperature loops. Let's thank Cary.
Thank you. It's something I appreciate you asking us to come here. If you can get the first, well, we got the first slide up. Really is after that whole dissertation by John, who was a team member, obviously, in this study. You know, it's what do you do with it, and how can we use it, and what advantages do we have? Because the state itself is interested in resource conservation, and basically minimizing the impact of whatever we do, and that includes carbon sequestration, water usage, etc. So we're going to look at it, and we're going to tell you just a little bit how we decided what we were going to do based on that. And I want to say one thing that add to John's, the consumptive right, which means the right we could pull out of that well and then send somewhere else, like the Jordan River, is 700 gallons a minute. The non-consumptive right is technically unlimited based on the reservoir. So we got a lot of ways to look at this and stuff. As John says, we pumped it and dumped it. We'd have a certain amount of energy we could use out of the system. But if we find other ways to utilize this thermal reservoir, we could probably expand it to 3 or 4 times fold its value, and possibly even more. Next slide. So first thing we did was we looked at the point project, and really we're looking at 3 different phases here. The initial buildings, which are being built right now, event center and a residential building in a hall, the meeting hall and stuff, about 794,000 square feet. Second phase is to develop a center of the project, or the hub as we call it, the major commercial district and residential district. And that's about 6.5 million square feet of buildings. And then finally, we move to full build out, where we turn around and integrate all of the things. So looking at those things, okay, next slide. Okay, we thought the best way to look at it is, and from experience at Weber State University, Colorado Mesa University, and around the country and stuff, the geothermal is quite adaptive. But usually you're looking in the background, you can see this picture of a house with all these ground connections and earth loops and everything. But the long short of it is that's conventional, and we're going to move past that. We're going to talk about using closed loop, which are called boreholes, not wells, but they handle source, sink, and storage of thermal energy. We have a conductive methodology of picking this up. We're talking about maybe warm boreholes and the ground source system. We have a convective, which is an open loop application, pump and dump or pump and re-inject. And then we had advective, which is using the water as it flows through the reservoir. Next slide. So we had to come up and start looking at it. The first thing we did was evaluate the heating and cooling loads. And we measured that in tons, which 1 ton is 12,000 BTUs and stuff. So this is an extremely large project that's going on. It comes up to be a total load of about 40,000 tons in heating and 49,000 tons in cooling. The cooling disparity has to do with the commercial buildings, which basically cool all year long. So we started to look at the reservoir, at the area assets that we had, that we could start to either pull heat from or dump heat into. So we saw domestic hot water, and that was an asset we had to look at. So we think about taking a couple of degrees out of, or adding a couple of degrees to the drinking water, and that is doable and legal. So we look at the wastewater, the black water, gray water, and everything. This is a great asset and stuff like that. And typically it's about 90% of the total water consumed on the building. We looked at well water, which is looking at a regular water well and pumping the water out of the water well. And then for conservation reasons, we re-inject it back into the same reservoir. So there is no use or no consumption to it. Then, of course, geothermal, which with John's numbers, we started about 2,500 tons, and we can start to look at how do we multiply that and more effectively use the resource. Then we have potable irrigation water, which is considerable, and domestic hot water that has to be made in the process of heating and cooling buildings. Then we have something special. It's called system diversity. And diversity is energy. When you put multiple buildings on a loop and stuff, I'm going to go into that. What happens is basically you can reuse that energy. And so in cooling, I throw energy into the loop. In the heating, I take energy out. And then finally, what we have is the typical geothermal of boreholes. And I'm picking up a lot of static. Good. Next slide, please. Anyway, if we look at it, the peak loads were 49,000 tons roughly in cooling, 40,000 tons in heating. We looked at combining all those assets, the renewable assets together, and putting in a backup, which would probably be natural gas and cooling towers. And the cooling towers, by the way, are water consumptive, but we would reduce them, and we would have about 70,000 tons of utility available to us. And if I just use the resources which were renewable, that list of resources I gave you, I actually can cover the entire load of this project, 49,000 tons of heating and cooling and stuff. So this is an indication that we could really make this whole project a renewable project with a backup for heating and cooling on the peak summer days or peak winter days. Next slide. So we came up with say, let's look at a different way to do this. How about a convective loop and a conductive loop that we use? It's a single pipe loop. It's closed in. It's a closed loop system, and they're different configurations. And if you go all the way to the right, you can see that you can turn around and link these loops together so that literally one drop of water goes around the entire system. It is able to do it. So all these systems be interconnected, but also like a water system could be modular, so that in case if you have problems with any of your system, you can shift it down. You can put it down, and the rest of the system doesn't go down. And you can subdivide these smaller loops, these minor loops. So this is really kind of a logical way to do this. And again, this is what we did at Colorado Mesa University and at Weber State University as two examples. Next slide, please. Okay, technical background real quick. This is district scale geothermal system. It distributes water to the buildings. The water is distributed in a closed loop system called the ambient temperature loop. The system of pipes includes the ground loops, the boreholes, and most of this is buried 10 feet below the ground, so it's not on the surface. And we can tap various resources, and they do not have to meet the total load. They can be additive one another, and we can put it on different heating and cooling loads.
Well, while we're trying to get them back, I'll try and go over. So this is what was done at Colorado Mesa University. What you can see is that there is a network of boreholes and surface facilities that are buried. And in the winter, you extract heat from the ground. You run it to a heat pump that is compressed, and it creates more heat. In the summer, you take heat out of the buildings, and you expand it through the heat pump, and it cools. Now, the interesting thing about Colorado Mesa University is that it has not turned on a boiler in 10 years. Okay, so substantial savings just because of this. And as Cary mentioned, a word we don't always want to use these days, but it's diversity. Okay, this is what takes into account the diversity of the buildings. So imagine that you've got an ice rink and a swimming pool. One of them you want to get rid of heat, and one of them you want to bring in. Now that's an extreme example, but sharing heating and cooling amongst buildings makes a huge difference in terms of the disposition of heating and cooling that is required. So you share and distribute the peaks. And
So John, will those heat pumps then operate simultaneously, or do they have their own capability of
so
heating?
everything that these days has process controls on. So you can have independent operation of the heat pumps for heating and cooling different parts of the district system. Cary can explain this better than I can, but that's my answer.
Am I back yet?
Yeah. Okay.
All right, we'll try to get it again. Anyway, John said, by the way, John, you did a great job. We can share energy across the buildings, and it's all independent. And because it's a single pipe loop, it's a plumb, what we call primary secondary. And that makes each heat pump, each building, and each asset on the loop hydraulically independent. It really kills the pumping power needed to run this thing, because you only use what you need when you need and how you need it. So, and then we can share energy over time with storage, which is the boreholes in particular. Now we add that storage component. We can turn around and stretch this to diurnally or seasonally. So we can, take some of the load off in the summertime, put it in the boreholes, and then night when it cools down, we can get rid of it if we need to. Next slide. So next, and punch through this, John. These are all the different kinds of assets that the loop lets you put on and lets you turn around and take it. And again, they don't have to be full size. They can be incremental and added to the whole same. One more click on the thing. And something that you look, and you see on the side, we have conventional assets that we could use, but it's quite resilient and quite adaptable. So now that we got a tool, let's see how we use it. Okay, next slide. So we subdivided the point into a sub-district. The red boxes are microgrids, or those boxes you saw off to the side. But if you look at the piping on it and everything, all of these microgrids, and there's 9 of them in this particular case, happen to be connected. So we can turn the microgrid on, we can turn it off, we can isolate it, we can do whatever we need to do it. And basically we've isolated the whole system like a potable water system. Next slide. Well, now that we got that, we can look and talk about what assets we're going to put on here. How about vertical boreholes, spacing 15 to 25 feet, depth is about 200 to 600 feet. These are closed loop holes in the ground with plastic pipe in them, high density polyethylene, and they are grouted with the thermal grout to aid in the heat transfer. We have to put trenches in to connect these, obviously, but they can be placed under landscape, parking, buildings, parking. It doesn't matter what it is. Next slide. So, and the next thing is we had to address what we could do with the thermal loop. What could we do with the thermal well? And we're really talking about a medium temperature to low temperature asset that produces a certain amount of energy. And the energy we start with is functionally 180 degree Fahrenheit water and stuff. We can take 100 degrees out of that, because this ambient temperature loop operates between the temperatures of 50 degrees Fahrenheit and about 95 degrees Fahrenheit. So it's safe. It's just regular water with low corrosion inhibitor and so forth. So we're starting to combine low temperature. The high temperature assets are bled into the loop in such a rate that the net resulting temperature is somewhere between that 50 and 95 degrees. Next slide. So, but now we'll take John's asset and we'll start to multiply it. What can we do? Well, direct use, we have pump and dump. That's at 700 gallons a minute that we talked about, and that's very limiting when you think about it. But how about pump and re-inject? If I put the water back in the reservoir and let it move on down the road and take new fresh water, and also start to reheat that water that's swimming, I just multiplied that asset by whatever the thermal reservoir can produce. And then we have indirect use of this, and what I call is a dedicated hot bore field array. And I'll show you where that goes anyway. But that's an array that produces only heat, but it's a closed borehole, and it might go 200 or 300 feet deep, and it's harvesting stuff. And then we also have another device called a closed loop advective device, which, by the way, looks a lot like that heat exchanger we saw in the first presentation and stuff. And that puts it in the moving water in the reservoir and collects heat as it passes. Next slide. Okay, so now all of a sudden we got a plan.
So now you can see the overlay of the geothermal resource, the potential to use that, boreholes within this heated area in the overburden that's there. You also have cold potential for cold water from regional wells or from wells to be produced for either cooling or heating running through the heat pump. So it's an integrated resource over the entire point. And basically, you can see that if you do the economics, natural gas and electric, the overall cost would building it would be about $25 million. And ground source heat pumps would be 13.7. Air source heat pumps are more expensive than any of this. And so what happens is you get the saving on pump.
Can you hear me now, John?
That's just me. You're good. Okay. Yeah. Thought I was being called home. You get a savings on electricity. You get a huge savings on water, and you get a savings on demand that consumers will implicitly and without knowing be imposing. And then certainly there's a reduction. The lowest CO2 footprint would be for the ground source, and natural gas would be about 2.5 times higher than that. So it's a very logical and feasible use of this thermal grid, where efficiency, you use 50% less energy, CapEx is going to be reduced substantially. You can leverage the existing geothermal system, and that has an advantage for low cost heating. You can use it for direct heat, and certainly it has some advantages for branding and things like this. And so all in all, it's a very reasonable use of heat. And so existing resources, the geothermal, the boreholes, the wastewater, all of those elements come into play to guarantee this. So I know we'll have to pretty much end this, but I'd like to thank, first of all, we'll start from the bottom up. We'll thank the state for enabling this feasibility study, the survey for providing all sorts of great information over the last 50 years for this. A number of folks at EGI, the party to whom this research was awarded, which is Diego Carroll with Geothermal Impact Alliance, Mark Smith with Sound Geothermal, and Rich White with his own company.